So this talk's mostly going to be based on a paper written by Guillermo, who was in my group a year before sort of I joined. And there's going to be some stuff I've been involved in, but yeah, a lot of it's Guillermo's work. So hopefully there we go. So just to sort of motivate the talk and the paper. If you're just doing simple mean square error regression, where the black points here are your training data, and the gray points here are some test data. The function is just like a sinusoidal function with some noise. You can see that a fifth order polynomial fitter does a reasonable job, because there are basically the same number of parameters as data points. The 50th order polynomial fitter does something kind of crazy up here because it's very highly expressive, and has no strong inductive bias. Whereas the one hidden layer neural network, the blue line, kind of sort of interpolates between the points. It does kind of the simplest thing you can do. And what I did here was take some sort of adversarial points, these red points, and got the same neural network to fit the black points and the red points. And clearly it can still fit the red points, and the black points. So it's not the reason why it fits this very simple function has nothing to do with expressivity. There's clearly some very strong inductive bias towards a function like this, rather than something else it can do. And this also easily seen in sort of real world data sets like MNIST and CFAR10. So we took binarized CFAR10 and MNIST and fashion MNIST, and if you just add corruption to the data labels, obviously when you get to completely random labels, it's not going to generalize, and zero corruption, it does generalize to varying extents depending on the complexity of the data set. But because it can fit these completely random functions, again, it means it's highly expressive. So there must be some form of inductive bias that makes it find functions that generalize well when it could find basically anything. So again, just to be an informal definition, the inductive bias is the properties of the model which determine what the outputs are of some given inputs that it hasn't encountered in training. So very standard stuff. So today I'm going to talk about Guillermo's approach to this, which was using algorithmic information theory. So I'll just lay out the sort of backgrounds of this, how Turing machines work, what Kolmogorov complexity is. Then I'll jump to his application of it to where he's sort of upper bound in complexity inspired by various results in AIT. And then we'll have a quick look at some more practical applications of these results, and do real neural networks actually behave how these bounds predict. So briefly, Turing machines are just computational devices. They have infinite memory, so this tape is infinitely long, and a finite state machine performing deterministic instructions, which are of the form, like depending on what's on the symbol under the head, it can change the symbol, it can move left or right, and then it'll change to a next state, again, depending on the symbol. And it will just keep on going until it gets an instruction to stop. And then we generally take the output to be the stuff that's left on the tape is typically considered the output. But again, there's loads of equivalent definitions. So each Turing machine defines some specific partial recursive function from input states where the inputs are the initial state of the tape and outputs are the final state of the tape. It's a partial function because it might not be defined on all inputs because there are infinite loops, and it's just generally the halting problem.
Sorry, what does recursive mean now?
So I think, recursive is just the next state. So the FSM will perform some action, and then the next action it will perform is dependent on like the initial state and then the previous action of the FSM, and then so on and so on and so on. So it's just recursive in the sense that the FSM just keeps on making new moves on the tape dependent on its previous moves.
Right. But in the context of this partial function, we can just think of that as like some mapping.
Yeah, basically. Yeah. That's not always defined on.
Yeah.
But we generally talk about prefix Turing machines, which work in basically the same way, but they have much nicer mathematical properties. So we have three tapes. We have an input tape, a work tape, and output tape. The input tape is write only, and you move from left to right, only from left to right. Sorry, the input tape is the program tape is read only, and you move from left to right. The output tape is write only, and you move from left to right. And then you have a bidirectional work tape where you can read and write. And you can the way I generally conceptualize it, the finite state machine in this context is kind of like the operating system, and whatever you've got written on the input tape is the program. And because you're only allowed to move to the right on the program tape, no program can be a prefix of another program, right? Because if you halt here, so this is like a halted Turing machine, if you're told to halt in this state, you're never going to be able to reach the next input part of the input tape, right? So it just sort of stops any program being a prefix of any other program. And again, we can think about this as a map from inputs, which in this case we generally think of as programs, to some outputs. And again, it's a partial recursive function because there are still halting problems, etc. And then we come to universal Turing machines, which again are just Turing machines, but we assume that the FSM is such that it could simulate any other Turing machine. So normally it's like on the input tape, the first part of the tape would tell the FSM how to simulate the FSM of some other Turing machine. And the Church-Turing thesis states that any computable function can in principle be calculated by a UTM. So the assumption is if you can compute it, you can compute it with one of these devices. And a universal prefix machine is the analogy for prefix Turing machines, although obviously any universal prefix Turing machine can actually simulate the behavior of any universal Turing machine, again, kind of by assumption, because if it's computable, you could compute it on any form of these Turing machines. But again, so they're very, very similar. But again, universal prefix machines have some very nice properties that we'll sort of exploit later on. And again, some programs can run forever. This is generally impossible to determine which ones will run forever ahead of time, which is the halting problem. Moving on to the idea of like complexity and how you can use Turing machines to characterize this. Obviously, probability theory cannot adequately capture complexity, as illustrated by these sequences. If you were to generate these just by coin flipping, like naught if tails, one if heads, each of these have the same probability of being generated, even though humans will obviously look at this one and say this one has a really obvious pattern. As illustrated by this, if you have the first sequence, you can just you can write it by just saying print 0, 1 n times. The next sequence is done by printing the binary numbers without any like delimiting characters. That's probably clear. And then the last one is pseudo-random. So you can't sort of compress its description any shorter than the actual length of the program. But probability theory can't adequately capture this. And arguably the first person to sort of adequately capture this was Kolmogorov and Solomonov. They both worked on this in basically in around the same time. And they came up with this definition. So if you have some string y, like on the previous slide, the prefix Kolmogorov complexity with respect to some prefix Turing machine, again, this is defined for both prefix Turing machines and non-prefix Turing machines, is the minimum length of the program that can produce this output, given that it's being run on a Turing machine. For the normal Turing machine, this program would be the sort of programming part of the UTM plus the input, and for the prefix Turing machine, it's just the length of the input tape. Again, because of the halting problem, Kolmogorov complexity is uncomputable, so it's not very useful practically. But it does have some nice properties, like if I have two universal Turing machines that are either prefix or non-prefix, the Kolmogorov complexity of the same output can only differ by some constant d. And the sort of intuition behind this is if I take universal Turing machine U and I want to simulate universal Turing machine V, that will take some amount of code to do this of length D. So I know that the cohomology complexity on Turing machine V must be less than or equal to the length of the program required to simulate U plus whatever the length of the shortest program on V on U that works. Is that clear? Or also do shout out with questions anytime, because I would definitely miss things by accident. If we want to think about how many strings are simple and how many strings are complex, there's a very straightforward counting argument, which again, it's kind of an analogy. Doesn't work perfectly because of the halting problem, but you can think about if you have 2 to the n binary strings of length n, then if I wanted to have some code that would compress these strings, there are only 2 to the n minus 1 strings shorter than this length. So we can have some sort of one-to-one mapping between like code word strings and the strings of length n. If you were to just randomly sample, strings, each of them has this probability 2 to the minus n, but the number of strings grows as 2 to the k. So if you plot the log of the number of strings, you get this sort of triangular structure up here, where half of the strings could only be compressible by 1 bit, and then half of those strings can only be compressible by 2 bits, and so on and so on and so on. It turns out that in practice, again, because of the halting problem and various other things, this is an overestimate. It's actually sort of 2 to the k minus the Kolmogorov complexity of k being the number of bits of the maximum compression you can do. So sorry, I should have this k here should be a lowercase k.
P is that probability?
This one, yeah. So it's like if you were to randomly generate the strings by coin flipping, each of the strings would have the same probability of 2 to the minus n. And then if I were to say how many, so I can either think of this as what is the log of the p of k, so what is the probability of generating a string of complexity k, or you can just think about it as the number of strings with complexity k, because there's uniform probability. So
that exponent is negative then?
Which one, sorry?
K minus k of k plus below 1.
I pose that this k here should be lowercase k. So I'm saying
probability.
That would be the probability of generating that complexity lowercase k upon randomly flipping a coin, because because almost all strings are highly complex. But by this argument, you would expect sort of half the strings to be compressible by 1 bit, and a quarter of the strings to be compressible by 2 bits, and so on and so on and so on. So you would expect upon randomly flipping, randomly generating these strings, there's a 50% chance that I'm only compressible by 1 bit. So you're over here. And then there's a 25% chance I'm compressible by 2 bits, and so on down the until you get to sort of, all compressible to n minus 1 bits. Yeah, sorry about the notation. That should be lowercase k.
So my question is that number less than 1?
Yeah, this number can be normalized, so it can always be less than 1. So it can be made as a probability.
So it's not probability.
So this number can be normalized. I just put the unnormalized one because you've got these order 1 terms. But yeah, sorry, should have been more clear about that.
What do you mean by the best we can do in practice, I guess?
So it's like if you have a Turing machine, so you can't, because of sort of self-delimiting codes and the problems with actual determinate, properly decodable codes, you can't have you can't use this sort of compression scheme on Turing machines. There's also the halting problem, which means you're not every program between 0 and length n is going to halt anyway. So there's going to be this minus k of k here, where it's the Kolmogorov complexity of the number on the order of the Kolmogorov complexity of the complexity that you're interested in here. You expect roughly this fraction of strings of these programs to not actually halt. So you have these types of problems. So again, this is very like hand wavy. There's lots of problems which I can't go into because of time constraints. I also don't fully understand like everything in the theory, I'm afraid. But yeah. Is it?
So yeah, so I mean, I guess like, so P here is not Kolmogorov complexity. This is really a tedious question, but I mean, what is P? Like what?
So as in P, as in this P here.
Yeah, exactly.
So it's, if you were to randomly generate a string, and then you were to look according to IID coin tosses, and then you to ask, what is the Kolmogorov complexity of this string? What is the probability that you would get some value of Kolmogorov complexity?
What do you mean by the probability you get? Like, so, sorry, the probability that that Kolmogorov complexity is equal to the
Is
K.
equal to this K should be lowercase.
Okay.
Yeah.
Okay.
Yeah.
Gotcha.
This may seem very like arbitrary and contrived, but this will be kind of useful later on for various other, like when we try to actually inspect how learning agents work, these types of like looking at these types of graphs will be quite useful. But sorry, that's why we're doing it. So again, another sort of test we can use, looking at it the other way around, rather than generating random strings and then asking what their Kolmogorov complexity is, we can generate, we can take one of these prefix Turing machines and we can generate programs, and we can then ask what is the distribution over string, what is the probability of getting a Kolmogorov complexity based on this process. And because the prefix Turing machines have are prefix codes, essentially, they satisfy the Kraft inequality, which means we can define a universal prior over possible output strings y using the normalization given by this expression, where the interpretation of this is, what is the probability of me getting some output string given randomly generated programs? So rather than randomly generating output strings, I now randomly generate programs which will produce these output strings, and then I ask what is the probability distribution over these outputs. Sorry. And thanks to a theorem from Levin, we can bound this universal a priori probability by 2 to the minus Kolmogorov complexity, plus at the bottom, because obviously the Kolmogorov complexity is the shortest program that produces this output, and the probability must be at least this big. There may be longer programs that generate the output, but we know that given that this is the shortest one that can, the probability must be at least this big. And Levin showed that there's some order 1 terms here, which are dependent on the universal Turing machine, but not the output string we're interested in. And then given the arguments on the previous slide, where we have the number of strings with complexity y, you have this exponential decay in the a priori probability. So you can say that the probability of generating some complexity given this type of process where you generate random programs is approximately uniform. So you get a uniform distribution over complexities if you generate programs by randomly flipping coins, basically. And again, this just illustrates the sort of how the universal a priori probability will scale. And this one shows, again, another quantity related to this that we'll look at later on for the practical learning agents. And then we can use this universal a priori probability to define a learning agent called a Solomonov induction, where again, it works in a very straightforward way. You have this prior probability over strings, and then if you were to show your learning agent some training string s of length m, and you were to ask it to predict the next parts of the string, it will take all of the strings, throw all the strings away if they're not compatible with the training string, and then just weight the rest of them according to universal prior probability. So it's massively biased towards the simplest program that produces the string it has. This has been stated to be the sort of ideal form of sequence continuation if the source is algorithmic. So people like Marcus Hutter have been pushing this and saying, this is the best way of defining, this best way of justifying Occam's razor, basically, is like pick the simplest function you can. And that there are various other people like Schmidt-Huber who's talked about a more practical form of this, where you have like a runtime term, because obviously if you were to write the source code of the universe and run the simulation, that would be potentially a very simple program, but it would take so long to run, it would be practically useless. And then various other people have come up with similar complexity measures when you have noise in your training set. So they'd say that the complexity of my program would be the length of the program plus however many bits I have to need to describe whatever noise is in my training string. But they all work in this type of way, where you have some universal prior probability, and then you just perform induction. So just to summarize, we have the Kolmogorov complexity of a string, which is the length of the shortest program that produces it. If you have a uniform distribution over programs, obviously you get a non-uniform distribution over strings, where low complexity strings are massively exponentially more likely than high complexity strings. And this sort of works out as you have a uniform distribution over complexities when you generate programs randomly. So on-and-off induction is claimed to be optimal up to these sort of order 1 terms when whatever the target string is algorithmically generated. And then one of the questions people have asked is, would this be optimal for practical purposes? If you're trying to learn some real world function, if it's algorithmically generated, then you should probably do it like this. And then lots of people discuss, like, are all real world functions we're interested in learning algorithmically generated, et cetera, but we're going to kind of take it as given that this is optimal learning in theory, that you should just pick the simplest description you can have. And then the question is, obviously, can you actually produce this type of learning agent? Because Kolmogorov complexity is uncomputable, so you can't even generate the universal prior. And obviously, it would just take forever, because most practical strings would be extremely long. So you could never actually do this process. Now we're going to look at Guillemot's work, where he produced an upper bound on complexity for various input-output maps, including neural networks. So I'll try and whiz through this because I realize it's taken a bit longer than I thought it would, sorry. So we often use this particular data set to do our experiments because it has a very nice complexity measure. So the Boolean data set is a function from binary strings of length n to 0 to 1. So you can describe it by an ordered bit string of length 2 to the n. So here are a couple of examples. So this is the 3-dimensional n equals 3 system. So you would have the inputs would be the corners of the cube, the 0, 1 cube. And then you can just order the inputs. So this one's 0, 0, 1. So it would go, that would be 1 in binary digits. There's 2, there's 3, 4, and so on and so on. So you can write down this sort of labeling of this particular cube just by an 8 long bit string, and you can very straightforwardly decode it and extrapolate back what this cube would look like. And here's just a second example in case this makes it clearer, where this first thing that was labeled 0 is now labeled 1, again reflected by 1 here, and this last the final bit that was labeled 1 is now 0, again labeled by this change. Is that clear how cool. So however, the number of actual functions grows extremely quickly. So I have, the output strings are of length 2 to the n, and then there are choice of, each of these can be 0 to 1, so you get 2 to the 2 to the n growth of functions. So there's sort of enormous numbers of functions. We generally use the n equals 7 system, where there are 10 to the 39, which should be big enough, we think. Almost all of these functions are extremely complex by the arguments we've given on the previous slide. previous section. And we can measure this complexity by taking the Lemperl-Ziv complexity, which is just it's a standard compression algorithm which works by taking trying to find little repeating chunks. And this seems, and we hope this will sort of approximate Kolmogorov complexity in a very loose sense, and it just seems to work quite well, so we use it. And then finally, the last thing we need to set this up is we have a proof that there's a minimum size neural network required to fit all functions, or at least this is so neural networks with these layer sizes are guaranteed to be able to fit every single possible Boolean function, just to make sure that these networks are fully expressive and any inductive bias has nothing to do with just them not being able to fit complex functions. So again, just to sort of visualize what these neural networks would be doing, we'd have some input space, which would be lowercase n dimensional, and an output space, which would be a single neuron, which we then threshold at 0. So, if you had, in the 2-dimensional case, you might have some decision boundaries, and we would interpret if it's on the blue side of the decision boundary, it would be a 0, and if it's above 0, then it's going to be 1 in a very standard sort of neural network way. We're going to focus on neural networks that are fully connected and have either ReLU or tanh activations, and then single output neuron threshold at 0. And then we can define a prior over parameters, which we hope is kind of somewhat analogous to the universal prior, again, very, very loose, where you have, we use the standard weight initializations. And then this generates a prior over functions by integrating over all parts of all theta, all parameter space weighted by this prior over parameters, if these parameters produce whatever function we're interested in.
Is there a minus sign missing, or is that on purpose?
There is a minus sign missing, I apologize, sorry. So yeah, this should be sorry, the best of theoretical physics. So we do this by considering the parameter function map, which is just the map from possible parameters to possible functions, or typically on our Boolean data set. So again, here's kind of a very vague visualization of it. We might expect some regions of parameter space will correspond to one particular function. And then, as we will see, typically this thing is very, very heavily biased towards some functions, and other functions it really struggles to fit. So this comes from Kamal, who is again in Ard's group even before Guillermo, who showed that the following holds for all computable maps, including parameter function maps, upon randomly sampling whatever parameters. So you can say that the probability of some output y is going to be less than 2 to the minus Kolmogorov complexity of y, given your map G and the size of the number of input points n plus an order 1 term. So for us, the map G would be the parameter function map. The size of y is the number of inputs in our Boolean hypercube, which also corresponds to the number of outputs. The number of inputs to the parameter function map is obviously the all possible parameter choices for neural networks, which we assume are typically discretized, but again, very, very loosely. And the number of outputs are going to be 2 to the n, which is the number of possible functions for our Boolean hypercube. And again, just to be clear, for the parameter function map, the inputs are actually parameters, and the outputs are whatever the functions the neural network expresses on the data set we've given it. And just to sketch out why this works, you can imagine an algorithm which would go over every single possible parameter choice in your neural network, map these inputs to their outputs, and record how many times I get some output. And then it would just print the resulting list of each output y and its corresponding probability. And then since we have G, the map, and N, the number of inputs are given, we have that this algorithm has complexity order 1, because it's not going to get more complex. The complexity is not going to grow as the size of N or the map changes. And we can use this probability to output map to compose a Huffman code for each output, and the length of the code word for each function or output is of this form. And then we can just simply rearrange this using the fact that this expected code word length has to be greater than or equal to the Kolmogorov complexity, because obviously I've got some algorithm that I could run in principle on a UTM, which has some order 1 complexity term here. And then I just need to feed in this code word here. And again, this Huffman code is a prefix code, so this could actually be done on a prefix UTM, although you'd be crazy to actually do it because it would take forever. And then you can just plug in this K into here, and you rearrange this formula, and you very straightforwardly get the upper bound back. Is that clear? And then actually, just for time constraints, I'll skate over this, but you can also show that there's a sort of statistical lower bound where you would expect most of the probability mass to hug this 2 to the minus k line. So again, in principle, the worst case is all we know is that the probability of some input y with some Kolmogorov complexity k is going to be less than this bound. But we have this statistical lower bound, which kind of suggests that most of the mass should exist quite close to this upper bound. And then finally, one other thing we've done is we've shown this will be useful later on when there's no obvious complexity measures, is if you have these types of algorithms, you expect to get Zipf's law. So if we consider algorithm A, again, where we just find this probability of y, rather than generating a Huffman code, if we just straight up rank order the strings by probability, so we get a string, a probability, and then a rank. So the most probable string has rank 1, the second most has rank 2, and so on and so on. We end up with another bound on Kolmogorov complexity of the output y, which is given by log 2 of the rank, because obviously if I have some number, log 2 of that is the number of bits required to describe the number, plus log 2 of the number of functions that have identical probabilities, because again, we're going to have find some way of distinguishing these functions, and there's some other log terms. And then if we make the potentially reasonable assumption that this bound is quite tight, we'll replace the less than or equal to sign with sort of a scales as for most y, so we end up with this. And again, we can just plug this into the bound 2 to the minus ky on the previous slide to get this, which again, when we simplify this, we end up with the probability of y should scale roughly as 1, or a constant, divided by its rank times the number of functions with the same rank. And what this looks like, if you plot this on a log plot, you get the log of the probability, like the log of the rank, will be a straight line with gradient -1. And again, this is like the third sort of litmus test we use to see, do practical neural networks actually work in this sort of with this complexity scaling form. Again, there are some conditions that Kamal said would make this bound be tight. So obviously the map must be very, very simple, because you're upper bounding the true Kolmogorov complexity with the complexity of the map and then the complexity of the input to the map by this Huffman code. So we need the algorithm to be very simple. G should be nonlinear, because if it's linear, there's no bias at all. But it should also not be chaotic. So a random number generator would generate pseudo-random, highly complex outputs. G should be highly redundant. So the number of parameter choices should be much, much greater than the number of possible functions. And the method of randomly sampling parameters should be sensible. So you're not allowed to just pick like one parameter and just like only sample from one very small part of parameter space. And he said that, and he evaluated loads and loads of different maps, not just neural networks. And he found that if these 4 conditions were met, we saw simplicity bias. You know, the outputs hug the bound rather than sort of being everywhere. And this is what Guillemot then found for practical neural networks. So if you look at the probabilities, this was on the Boolean system, the hypercube, and he found that you get this so each of these data points is a possible function. The y-axis is the probability of the function, and the x-axis is the length-positive complexity. And you can see that like it actually follows, and this red line is the upper bound. And you can see it does a reasonable job. Most of these points lie underneath the line, apart from this one. These ones have where it does seem to border quite nicely by length-positive complexity. This plot shows the frequency. So this is P of K. So this is the probability of getting some length-positive complexity upon randomly sampling neural networks. And again, you can see it's kind of flat and it tails off at the end, which is what was predicted earlier on. And then finally, this is what happens if you plot the probability of a function, log probability of a function by its log of its rank. And again, it's approximately, it's sort of Zipf's law like, you get this -1 exponent. And this was from Guillemot's paper in 2018. So any questions so
So
far?
is it sensitive to the selection of the prior on square? Did you really need the Gaussian or whatever sigma square?
So we found if you use uniform initialization with ReLU, or if you use any sigma W with ReLU, because it's scale invariant, it's completely insensitive. Uniform, it's very, very similar. There's like small deviations, but in general, very similar. What we will comment is what happens when you use large sigma W with Tanch activations, because obviously if you have deep neural networks and you have large sigma W, you push yourself into the chaotic regime. And this seems to break the simplicity bias, which I think I've got. Yeah, I've actually got this on the next slide. Great. So if you use, so these ones are 10-layer Tanch activated neural networks, and we use different values of sigma W, so the weight variance initialization. And as you move towards the chaotic regime, you can see, so these blue dots, again, so I've overlaid these plots here. So the blue dots will carry on behind these. So you can see that again, you get this nice sort of 2 to the minus K plot here, and then you slowly sink down as you move into the chaotic regime. By the time your sigma W equals 4, you never find one function more than once. So you can see these little purple dots here. By the time your sigma W equals 8, you again never find the functions more than once, and you never really find any functions more simple than complexity of 65 in 10 to the 8 samples. And for comparison, the green, you just randomly sample strings, you never find a function simpler than about 90 or 100. And again, the Zipf's law starts to break as well. It's quite hard to tell, but these lines will slowly fall off to completely flat. And this will be more clear in some later slides for more practical data. And again, this P of K distribution, which this is the ordered prior, behaves roughly as you expect. The chaotic prior, as you can see here, starts to fall down from this uniform in complexity. And then the green, the complete, and then just for comparison, here's what happens if you just randomly sample over strings. You get almost all complex, and you can say there's only 2 simple functions. There's only the all zeros and all 1 function has length-positive complexity 7. So we know there's only 2 down here. So we know that this line must sort of end up coming down here sort of like this. And this triangle is just a sort of theoretical what would happen in the optimal compression case. And then the question is like, why is the upper bound not tight for chaotic neural networks? Why is this chaotic condition required? We're currently not entirely sure, because it's still a very simple map. It's not really any more complex to do the Huffman code generation via this method with sigma W equals 8 than it will be sigma W equals 1. So we're still thinking about this.
What's the ideal picture? Like what would be good and what's bad? So flat.
Flat is good. So So P of K, if P of K is flat, that implies generally that you have a strong bias towards simple functions, because you have like an exponential growth in complex functions, but an exponential decrease in the probabilities each of those complex functions is assigned. So you have like 2 to the K growth in functions, but a 2 to the minus K growth, 2 to the minus K drop off in the probability given to that function. So if you have that case, which we say is kind of optimal, or somewhat close to optimal, you get a flat distribution here, which would correspond to.
Okay.
Yeah. Sorry. But obviously these are just essentially priors, right? We don't know, does this actually translate to posteriors, because SGD is not a fully Bayesian sampler. So again, just to sort of illustrate what happens, and then we'll look into like exactly the correspondences. You could use this prior probability to construct a Bayesian learning agent, exactly how Solomonoff induction would work. And if we approximate this, because doing this requires MCMC methods or Gaussian processes, which we've done Gaussian processes and we get very similar results, which we'll come on to later. But if you just use a standard SGD and you use different priors and then you train to different target complexities, the neural network is only capable of generalizing well for very, very simple targets, and it gets obviously progressively worse until it's completely incapable of learning random targets. The chaotic neural network, again, is sort of slightly better, is much worse, but it's still slightly better than a completely random learner, which obviously you can just theoretically show has this.
And then those are, the change is essentially the sigma.
Yeah, exactly. Just like how far into this chaotic regime are you? Yeah. So for now, we hope that using SGD kind of approximates this sort of ideal Bayesian learning agent, and we'll talk about this a bit more later.
And you train them until you get
zero training error. Yeah. So we take 64. So of the 7-dimensional hypercube, we take 64 out of 128 of those as training data, and we select these completely randomly. And then we calculate the complexity. We have some complexity of the overall target, and then we just measure the generalization error. And another illustration of the inductive bias, again going back to the beginning in neural networks. This system so this is for n equals 5, but because there's only 4 billion functions, we can actually enumerate over all of these. So what this plot shows is if I were to go over all of these functions, and I were to eliminate all functions with an LZ complexity greater than, for example, 20 here, what would and then I were to, of those functions, I would only pick the ones that have zero training error or minimum possible training error. I would then give them a uniform probability of being correct, and I would calculate the generalization error of that learning agent. If I do this where I have a uniform probability over strings with minimum training error, I get classic bias variance behavior, right? As I increase this cutoff, I allow more and more complex functions. I get much, much worse performance until it's 50%. But because the neural network, the ordered neural network, has a very strong inductive bias, the probably suppressed, that I can increase this cutoff and I don't have enormous, generally, I don't suffer enormously in terms of error. Obviously, if I have a completely random target function, which is, so this is the value of the target here. This was completely randomly generated. Obviously, I don't get any bias variance trade-off because it's just, you're never going to learn the complex function no matter what you do. And then I'll try and skim through this really quickly because we've only got a couple of minutes. So in summary, we've got this empirical upper bound. We can show using these Boolean functions and lambdas of complexity, this bound appears to hold somewhat, predict qualitatively the right behavior. We get Zipf's law, again, very tentatively because there's some sort of very uncontrolled approximations in the formulas. And again, using sort of the Solomonoff induction inspired posterior standard Bayesian neural networks, this could help us sort of understand how generalization works. And now we have to test, is the probability of finding a function with SGD kind of similar to this idealized Bayesian learning agent. And we can do this on large scale data sets by, so for example, so you have some data distribution D, P of X and Y. So for example, we could have X would be MNIST, so this D would be the MNIST data set. So the X would be some images and the Y would be some labels. And we can have different discretized functions where we just represent the functions rather than by the raw values of the neural network output. It's just, are you correct or are you not correct? Like what classification do you give each of these labels? So again, we can sample a training set from this. And then in order to discretize the function, yeah, we'll do it by this method where we have, it's just a correspondence between images and labels, no probabilities, completely discretized. We know from a paper by Gadi-Naver that if you have infinitesimal gradient descent, weight decay, and white noise, you get a this probability of gradient descent is actually a perfectly Bayesian posterior. And in the infinite width limit with NTK parameterization, you get, again, other possible Bayesian posteriors. I'll just skip this briefly and come back to it at the end. And then the question was, do these like insights from people like Gadi-Naver actually work for finite learning rate optimizers? And we used Gaussian processes to estimate the posterior, and compare this to SGD. So the way these experiments work, you take some training set size, in this case 10,000, and we take 100 test set images. You train until you're 100% accurate on the training data, and then you look at what classification is predicted on the test set. So each of these data points represents a possible way of classifying the one of the test points. So this function here, it has one error on it. This is the completely true function. You can see it, doesn't generalize perfectly. It finds this one error function with highest probability. But it follows and the y equals x line is, all the points would lie roughly on the y equals x line if P of SGD were to perfectly equal the Bayesian posterior probability. Again, this just illustrates you get another exponential decrease in the Bayesian posterior as a function of generalization error. So there's no good complexity measure for any of these functions. But again, we can see that as you get worse generalization errors, the probability in the Bayesian posterior decreases by sort of 200 orders of magnitude. And I'll just skip the CSR because that's not a very good complexity measure. We did some other things where we looked at various different batch sizes and learning rates, and we found that no matter what you chose, you got reasonable correlation between p-Bayes and p-SGD, but you could quite substantially affect the correlations. They always seem to be log linear. So we did about 60 of these experiments just to confirm this wasn't a fluke. And no matter what we did, it was always pretty log linear, but depending on the optimizer hyperparameters, there was quite a big difference in slope. And this is CFAR 10. For more complex data sets where it generalizes worse, you get a less good correspondence. But if you look at the number of orders of magnitude here, it correlates fairly well. So yeah, there's some pretty heavy limitations of these experiments. So we can use this discrete function space picture to coarse grain, but there's a lot of other interesting like loss related details that this doesn't really capture. There are a lot of experiments, lots of architectures and data sets, but they're all, they're comparatively small scale. We can't do this on ImageNet. And we know that the effects of feature learning become much more important when you have large scale data sets and very deep architectures. And the question is, how much does this actually affect this sort of very coarse grained, very general arguments? So in summary, these experiments and the sort of theoretical bounds sort of suggest that the priors will be exponentially biased towards simple functions. SGD appears to approximate a Bayesian sampler, at least in these fairly small scale systems. which, put these two observations together. This might sort of point towards a way of thinking about why neural networks generalize. But there are obviously lots of problems. The Levin upper bound is only the Levin inspired upper bound, sorry, to be clear, doesn't provide any very specific mechanism. It just says if you have a highly parameterized system, many more parameters and data points, and it satisfies a bunch of requirements, then you would expect to see strong inductive biases towards simple functions. But there's other more sort of proper causative mechanisms where you can look at these functions without coarse graining, and you find that there's the eigenvalues of the Fisher information, for example, are vary over many orders of magnitude. So suggesting that they're also effectively low dimensional, which sort of would correlate with simplicity, but in a more like fine-grained picture. And then finally, understanding the relation between optimizer hyperparameters and the emergence of feature learning and its sort of importance layered over the top of these very general arguments is very much something we're looking into. But yeah, these arguments don't actually answer that. And yeah, so that's it. And thanks to all of these people who worked either with me or on the arguments before I came into this group. So yeah.
Is this convergent complexity related to entropy?
Yeah, so I'm trying to remember exactly the relation. So it's like if you have entropy, if you have a source generating inputs with different generating inputs with sort of IID probabilities, and there's some probability distribution over these inputs, then I think the Kolmogorov complexity of describing the outputs from that source is either the entropy or very closely related. Okay. But Kolmogorov complexity can obviously deal with, entropy wouldn't deal with a string like, I'll try and go all the way back to, entropy wouldn't deal very well with as I understand it at least, entropy wouldn't deal very well with a string like this, which is very high, it's very high entropy, because you can't generate it with an IID source. But Kolmogorov complexity can capture the fact that this is actually quite simple. Sorry, that wasn't a particularly good explanation.
You like the bounds you gave, they're very similar to so there's a result called the Shannon-Macmillan-Riemann theorem, which tells you that if you take a random sample from an IID sequence and you evaluate the probability of a random sample from an IID sequence very tightly concentrates around its entropy up to the length of the sequence. And that looks very similar to the bound we have with this model.
I'm not familiar with that, but I'll definitely look it up and try and understand it.
So can you give the UI just to design better neural net?
Yeah,
the ultimate goal.
Yeah, I think the problem with these arguments is just they predict. So they wouldn't, for example. So actually, just skimming forwards. I skipped over these Zipf's law experiments here, but these arguments these arguments would predict Zipf's law no matter where you are. You get so we've taken the same architectures in different data sets, and you get Zipf's law in all three cases. So the only difference is obviously because I have different, actually it's probably more easy to see here. So we've got the same data set CFAR10 and three different architectures. They're all roughly Zipf's law, but because they generalize differently, we know that the ordering of the functions is massively different. So the problem is these AIT arguments don't really distinguish between exactly what the measure of simplicity these networks see is. They just say that if they have this particular, massively overparameterized property, they will be biased towards some type of simple functions for some definition of simple. So unfortunately, I don't see an obvious way of taking these arguments and saying, okay, and now we can make a better dense net, for example.
So similar question, but not necessarily can use to design better networks, but how do you think of neural networks before versus after this? Like, is there a big difference in your own?
Oh, in my own conception.
Yeah.
I mean, I guess I tend to think of them as, I just tend to think of parameter. I tend to assume that SGD is kind of approximating these Bayesian a Bayesian sampler. You have a parameter space that has large regions corresponding to very simple or very low dimensional functions that you're just much more likely to stumble on when you're using SGD. And then there's some various results by people like Greg Yang and Barretin who've shown that depending on hyperparameters, you can encourage the feature learning properties, which are somewhat similar. Again, looking at Barretin and Oymak, I think, showed that their feature learning is somewhat strong. Feature learning generally correlates with even simpler functions by sort of dimensionality estimation. So you can kind of further improve on this really strong bias. But yeah, I generally have this picture in mind. That's kind of how I think about them now. And then also with the Zipf's law, where you have the same data set, different architectures, and they will have their own sort of intrinsic sense of what complexity is. And yeah, that's kind of how I think about them now.
So you said a couple of times like the chaotic region. What do you mean by that?
So if you have so if you take a neural network with tangent activations and you have very, very large weight initializations, you can prove that in the limit of infinite depth, the outputs become perfectly chaotic. So it's like if I have two inputs that are some small distance from each other, then there's no correlation between the outputs. Soufiane actually worked on this. Soufiane actually showed this for NTK. Yeah, so we use this as a test of, obviously we see this very strong bias in normal neural networks, but then we need some way of actually breaking the bias. Otherwise it might be this, this just happens everywhere and it can't explain generalization or doesn't even correlate with generalization at all. So that's why we generally use these chaotic systems as a kind of sort of litmus test. Yeah, this stuff is actually new. We're looking to publish this in the near future, but I take a long time writing code, so. Thanks.
If there's no more questions, thank you, Chris.